We're now going to look at how double integrals can be used to calculate moments and centers of mass. Let's recall from Calc 1 that a moment is the product of the mass multiplied by the distance that that mass is away from the fulcrum point. So essentially mass times distance. Let's let m sub o be the moment of this system about the fulcrum point. And to get the moment about the fulcrum, we would simply add together the individual moments, basically to get the tendency to rotate about that fulcrum point. In order to determine the center of mass, we need to get the total mass of the system, and in our scenario, we would get that by just adding up the sum of the two masses. And then the center of mass can be calculated by taking that moment of the system and dividing by the total mass. So back up here in this scenario, let's assume that mass 2 is greater than mass 1. And when we calculate that center of mass, it would end up being somewhere in this area. This is the point where we would need to put the fulcrum in order to balance the seesaw. Now let's see how we'd calculate the moments and centers of mass in a two-dimensional scenario. Here we're going to talk about the moment about the x-axis, which can also be interpreted as the tendency to rotate about the x-axis. And as well, let's discuss the moment about the y-axis. The moment about the x-axis is going to be calculated by looking at the mass of an object multiplied by the distance that that object is away from the x-axis, so in this case y1. But we need to consider this for every element in the system. We'd need to add mass 2 multiplied by its distance from the x-axis, which is y2, and mass 3 times its distance away from the x-axis, which is y3. When we add all of this up, it gives us the moment about the x-axis. Similarly, in order to get the moment about the y-axis, we're going to add the individual moments, which is going to be determined by mass 1 times its distance away from the y-axis, which is an x-coordinate, plus mass 2 times its distance away from the y-axis, which is x2, plus mass 3 times its distance away from the y-axis, which is x3, and this gives us our moment about the y-axis, or the tendency to rotate about the y-axis. Now, in order to get the center of mass, we'll need to first determine the total mass of the system, and the total mass of the system is simply going to be the sum of each of those individual masses, which can be expressed using summation notation like this. Now, in this scenario, our center of mass is going to be an ordered pair, where the x and y coordinate calculations are similar to the one-dimensional scenario, which is just that in order to get the x coordinate, we're going to take into consideration the tendency to rotate about the y-axis, and then divide that by the total mass. In order to get the y coordinate of the center of mass, we're going to take into consideration the tendency to rotate about the x-axis, and divide that by the total mass. Now, when we're trying to calculate the moment and center of mass of a lamina, where the mass of the plate is not consistent throughout the entire plate, there is a varying density function representing the density of a particular point. So the density at this ordered pair down here might be different than the density of this point up here. So the entire plate has a varying density function. And so when we're trying to calculate the center of mass, this is where we would need to bring in our double integrals to add up infinitely many different masses. So in order to calculate the moments in the center of mass, let's consider an arbitrary rectangle somewhere inside this lamina. And let's choose an ordered pair representative for this rectangle, where the x-coordinate we'll say is some x sub I, and the y-coordinate is some y sub j. And then let's call this the Rij rectangle. And let's figure out what the mass of the Rij rectangle would be. Well, to determine the mass of this rectangle, we need to consider the mass density and multiply that by the area of the rectangle itself. So in this case, we'll say that the mass density of this rectangle, if it's infinitely small, well, most of the masses are going to be approximately the same as the mass of the ij ordered pair, so we'll just let that x sub I, y sub j representative be the point that determines the mass of the entire tiny rectangle, and then we'll multiply that by the area of the rectangle, and again we'll use delta A to represent that small area. So let's consider the moment about the x-axis of our tiny rectangle, which is determined by the mass of that rectangle multiplied through by the distance that it is away from the x-axis, which is rho evaluated at x sub I, y sub j, times delta A, which gives us the mass, and then we multiply that by the distance we are away from the x-axis, which is y sub j, this distance here. Now similarly, if we want to look at the moment about the y-axis, the tendency to rotate about the y-axis of our little tiny rectangle, which is calculated by looking at the mass of the rectangle multiplied through by the distance that it is away from the y-axis. And again, the mass of our rectangle is this mass density function evaluated at x sub I, y sub j, multiplied by delta A to give us the total mass of the rectangle, and then we multiply that by the distance that we are away from the y-axis, which is this x-coordinate, x sub I. And now in order to get the moment of the entire system, we need to add up infinitely many different little tiny rectangles. And this is where our double integrals come into play. So the moment about the x-axis is going to be considering the mass of that little tiny rectangle multiplied through by the distance that rectangle is away from the x-axis, which is a y-coordinate. The moment about the y is going to be the mass of the little tiny rectangle multiplied through by the distance that that rectangle is away from the y-axis, which is an x-coordinate. And then in order to calculate the center of mass, first we need to get the total mass of the system, which is essentially just adding up all the masses of the little tiny rectangles. And again, we'll see to get the x-coordinate and the y-coordinate of the center of mass, which is an ordered pair, we'll take the tendency to rotate about the y and then divide that by the total mass, and then the tendency to rotate about the x and divide that by the total mass, which is given by these formulas here.